Hello participants, welcome to the day 4 of the e-learning course on chromatography. Your feedbacks that came yesterday on the basis of the HPLC lecture and the MCQ test were really interesting and encouraging. Few of the questions I have answered and few questions are yet left to answer. Especially the question number 4 and the last question of the MCQ test had some queries. Question number 4 query was solved through a message, but I am now planning to compile all your questions and come out with a separate lecture. So friends, let us begin with today's topic, and that is ion exchange chromatography. Friends, when we talk of ion exchange chromatography, it is a concentrated topic to only few aspects around science. So friends, ion exchange chromatography is mainly dealing with separation that is based only on electrostatic interactions. So this is the major advantage of this technique, that you do not have to focus with all samples, or all samples cannot be tried in ion exchange chromatography. Segregation of only those samples are possible in ion exchange chromatography that have the capability of going through electrostatic interactions. So cations and anions. Apart from cations and anions, charged biomolecules like protein, peptides and amino acids. Now, how amino acids can be a question of doubt. You know, when you study amino acids in biomolecules, you generally use the word zwitterion. And when you say zwitterion, it is not in the normal state of amino acid, but it has NH3 plus and a COO minus end. Hence, it is a charged biomolecule. So, separation of analyte on the basis of net surface charge of the molecules. The phenomena occurs in the column is electrostatic interaction. In IEC, that is ion exchange chromatography, the stationary and the mobile phase in general can be as below. Stationary phase is generally a solid resin and a mobile phase is a liquid. Now here, as you are interested in catching up cations and anions, your resin must be oppositely charged. Then and then only electrostatic phenomena will occur. And henceforth, there are two types of resin available: cation exchange resin and anion exchange resin. Principle behind ion exchange chromatography: a very simple phenomenon. Molecule possessing opposite charge will bind, means molecule possessing the opposite charge as the resin will bind tightly to the resin, whereas molecule having the same charge as the resin will flow through the column. Here it means molecules relates to the analytes, the sample. The sample possessing the opposite charge to that of resin. Resin is a stationary phase. Will bind tightly to the resin. Means if a molecule is a cation, it will bind to an anion resin. Whereas a molecule, if is a cation and your resin is also a cation, it will not bind. So over here, this charge inside the circle is a stationary phase resin, and these charged molecules are our samples. They will bind because it is opposite. They will bind because it is opposite. So when your resin is a positively charged material or a stationary phase, it will always catch anions. Hence, a positively charged stationary phase resin column is always called an anion exchanger, whereas a negatively charged stationary phase column is always called a cation exchanger. Friends, there are two approaches in operating ion exchange chromatography. One is the rational approach where you have a glass column and you do all the work manually, whereas the same phenomena can be performed in a very small stainless steel column which can be embedded in the HPLC system. It is called a derivatized approach. If you remember the day 3 talk on HPLC, I had made a clarity over there that four types of chromatography based on mechanism can be performed using HPLC. One that we focused yesterday, that was day 3 of this online course on chromatography, was reverse phase and normal phase. There itself I have mentioned, if you have looked carefully, the second one was affinity, the third one was size exclusion, and the fourth one was ion exchange chromatography. So let us take the column capable of exchanging ion in the form of cationic exchange resins and anionic exchange resins and put them in the loop of an HPLC machine by replacing just the column. Henceforth, if we go with the separating mechanism, here you will see a very interesting example. Over here, there is a picture of a column. Both columns are the same. This picture is at the initial stage. This picture is after some time. If you look into this very tiny box, you can see that positively charged ions in their increasing strength are given. The ions with the dark greenish color have the highest positively charged strength, where the light green are mid positively charged ions and the lightest green towards yellow has the least positively charged attraction. Your resin is totally negative. Now see, your resin is negative, your column is negative, your stationary phase is negative. So it will always attract the oppositely charged ion. And even in that, the oppositely charged ion with the highest power will be attracted the most. So over here from the picture, the dark green molecules or samples or analytes will be attracted the highest towards the negatively charged resin, and as and when you move down you can see the least positively charged resin are attracted the least with the negatively charged resin, and such negatively charged resin are called cationic exchangers. So over here, this is the mechanism on which ion exchange chromatography works. The picture can be explained as written. A cation exchange resin carries a negative charge and therefore ions carrying net positive charge bind to the resin. The impurities or the components which are neutral or carry negative charge do not bind because here two negative charge will not bind to the cation exchange resin and elute with the mobile phase. But among the three positively charged ions, the ions which has the strongest positively will tightly bound and the ions with the loose or the least positivity will bind less, and the one that bind less will move along with the column will move along with the mobile phase to the end of the column and will go out first, will elute out first. So the green molecules with the highest strength are still inside, whereas the yellow or lightish green molecules are going out because of the least affinity, least attraction, and that attraction is only electrostatic attraction. So friends, this is the main mechanism on which the ion exchange chromatography performs. Dual mechanism is observed. What do we mean by dual mechanism? Ion exchange due to ionic attraction. It means there is attraction between a negatively charged resin, and resin over here are stationary phase, and a positively charged sample, which can be explained over here. Exclusion of ion due to repulsion between homogeneously charged analyte ions. It means if I am passing a positive and a negative ion from a column, and the column is itself positively charged. So the negatively charged ion from the mixture will attract towards the column because the column is positively charged, electrostatic attraction. But at the same time, the negatively charged ion will move away. Let me explain it again if there is some error. Let us assume my column to be positively charged and I have a mixture of positive and negatively charged ions. If my column is positively charged, among the positive and negative, the negative will attract. Whereas the positive sample will repel with the positive because of the same electrostatic force and will move away fast. So there is a dual mechanism, a mechanism of attraction between the oppositely charged ions and the mechanism of repulsion between the same charged ions. And due to the repulsion, the repelled ion will move out quickly and will elute first. This can also be observed from this graph. If you look towards the graph, in this graph, protein A and protein A is eluting out first and protein B is eluting out second. It means protein A carries the same charge as stationary phase and does not bind. If your stationary phase is a plus and if your protein A is a plus, it will not bind. It will move away. Electrostatic repulsion. So let us assume over here that our stationary phase is a cation, means it is an anionic exchanger. It itself is a cation. So if analyte A is a cation, it will repel and A will go out. Whereas B is less cation or more anion, then it will bind. So here you can say protein A carries the same charge as stationary phase and do not bind, whereas protein B binds and is eluted later. So this is the two slides, that is dual mechanism in IEC and separation mechanism in IEC, the main theme or the main chemistry behind ion exchange chromatography. Types of ion exchange chromatography. There are fundamentally two types of ion exchange chromatography: cation exchange chromatography and anion exchange chromatography. Now, what is the main factor that controls the ion exchange? Over here, you have ionic charge, means plus 1, plus 2, plus 3, plus 4, and you have ionic radius, that is R. So, when you take the ratio of ionic charge Z and ionic radii R, you get ionic potential. And remember, friends, the higher the ionic potential, that ion will bind strongly with the stationary phase. Let it be cation, let it be anion. If a cation has the higher value of ionic potential, it will bind tightly with an anionic stationary phase. And if an anion has the highest value of ionic potential, then it will bind strongly with a cationic stationary phase. And as we know a little mathematics, in Z by R, the lower the value of R, the greater will be the value of Z by R. And henceforth we can say smaller the radius, smaller the value of R, smaller the value of denominator, larger the value of ionic potential. Similarly, more the value of Z, more will be ionic potential, because Z is directly proportional to ionic potential and R is inversely proportional to ionic potential. Therefore, more the value of Z, that is higher charge, less the value of R, smaller radius, results into high ionic potential. And remember, more the ionic potential, more is the attraction with the stationary phase. But this can be summarized in a very simple way, not for general ions, but for hydrated ions. Friends, here is a chemistry of hydration, which is very important. Generally, when we say that I am separating a mixture of ions, it does not mean you are taking only sodium plus, calcium plus, magnesium plus, mixing and separating. But they must be soluble in some solvent, and that creates a hydration phenomena. If we take a mixture of ions in water and allow it to pass. Then hydration phenomena occurs. And what are its impacts? We will see. But before going into that, let us create a nutshell of this very important slide. Anion that are in hydrated state with a high charge and small radius will bind strongly, whereas cation in hydrated state with a high charge and small radius will bind strongly. So friends, the common theme that comes out is the charge should be high, the radius should be small, and the ionic potential generated will be too large, which will be helpful in binding strongly with the stationary phase. Depending on this, we have a very important example to learn. We all in our undergraduate course have heard of separation of lanthanoid ions. If you look into that experiment very carefully, or if you recall that experiment, friends, at the end of the experiment, lutetium is the ion that comes out first, and lanthanum is the ion that comes out last, pertaining that all the ions in the lanthanoid series are in the +3 states. It means we are not now concerned of the charge. We will not talk of Z because Z is common +3. We will only focus on R, radius. If you remember the topic, lanthanoid contraction, moving from lanthanoid to in lanthanoid from lanthanum to lutetium, the ionic radii decreases, and hence we coined it as lanthanoid contraction. But that decrease in radii is when the ion is in independent state, means imagination of a lanthanum ion alone by removing 3 electrons. So, when you have a naked ion or an independent ion, then moving from La3 plus to Lu3 plus, the size shrinks. But you might be aware of a very basic school concept that when you hydrate these ions, their size get reversed. Means now lanthanum when was in a naked state +3 state was the biggest or the largest in radii, and lutetium or lutetium was the smallest in radii, but in the hydrated state it becomes reverse. And so the lanthanum 3 plus becomes the smallest in radii, and the lutetium 3 plus becomes the highest in radii. Mind well, I am not speaking independently, naked. I am speaking in its hydrated state. The case get reversed. So in hydrated state over here, now lutetium is the biggest and lanthanum is the smallest, and therefore as we know, smaller the R, higher the ionic potential, and therefore lanthanum in its hydrated state has become the least in radii, and therefore it will have highest ionic potential and it will bind strongly. So as it binds strongly, it will remain in the top part of the column. As and when you will add, it will bind thoroughly. But lutetium, which has now been more in radii, larger in radii due to its hydrated state, will not bind strongly. So the one that does not bind strongly move downwards with the flow of mobile phase. So you can say that lutetium is coming down and lanthanum is remaining on the top when when they are in the +3 hydrated state. And therefore if you imagine lutetium is at the bottom, lanthanum is at the top. So when you will try to elute it with the excess of mobile phase, lutetium will come out first and lanthanum will come out last. Friends, this is what is explained in this graph. If you see this graph properly, you can see somewhat around the initial 4 minutes, lutetium 3 plus ion has come out. But at last, lanthanum 3 plus ion comes out. So this is how ion exchange plays a key role. But don't get confused. I have explained this example of lanthanoid separation in their hydrated states. So this is one of the best application over here. Henceforth, the order is reversed over here. Generally, the order is when we move from lanthanum to lutetium, the size decreases. You are right, but it is independent plus 3 charged ion in the naked state. But here I am talking of hydrated state, and therefore the order is reversed. Ionic radii is reversed in hydrated state. Hope you have got this. If not, if you have any error, you can mail me at this instant. I'm speaking it deliberately. I will give you a very wonderful practical proof from a company's data. Distribution coefficient. Over here, the difference in the binding affinity of the analytes, that is the ions to be separated from the mixture, can be used to calculate the theoretical effectiveness of the separations. This can be done by comparing the distribution coefficient. It is very easy. Which cation or anion will be highly separated? The cation or anion that spends more time in the stationary phase. It means the sample which is distributed more in stationary and less in mobile will have the best theoretical separation. If you look over here, D is the distribution coefficient value. The distribution coefficient is the ratio of the concentration at a steady state of the ion on the stationary phase to the concentration in the mobile phase. So the numerator is stationary, the denominator is mobile. So the more you are in the stationary phase, the more is their distribution coefficient value. So in resin, ions of interest have higher value of D, and higher value of D means they are strongly binded to the stationary phase, because more you are in the stationary phase, solid support, more you are in the CS, and more you are in the CS numerically or mathematically, more you are in a numerator, and when you are more in a numerator, the D value is more. So remember, in distribution coefficient, if you are interested in finding the cation of your choice getting attached to the stationary phase, it should have its concentration more in the stationary phase and resulting into higher value of D, that is distribution coefficient. Friends, stationary phase and the factors affecting its performance. Resins are spherical beads typically made up of inert polymeric materials. So resins do not react. But over this resin, there is a suprafacial coating of cation for anion exchange and of anion for cation exchange. And this takes part. So resin made up of inert polymeric material are support on which you are going to coat the stationary phase. But this coat is not liquid coated on solid, it's a solid powder. Resins are spherical beads, typically made up of inert polymeric materials, providing the facility to coat negatively charged surface or positively charged surface. And you know, when you want to extend negative charge, you call it as anion exchangers, and when you want to exchange cation positively charged, you call it cation exchangers. And now, if you are interested in exchanging negatively charged ion, you require cation exchangers. And if you are interested in exchanging positively charged ions, you require anion exchangers. But what are the factors that will affect this exchange phenomena? Surface area. More the surface area, more will be the exchange. More the density of the cross linkage, that is functional group, more will be the exchange. If your anion or cation exchanger is a very high negative values or very high positive values, it will be a good exchanger. Friends, these are the two important factors that affect the performance of a stationary phase. Groups present on a stationary phase. These are fundamentally the functional groups that are present on the stationary phase. Aminoethyl, diethyl aminoethyl, trimethyl aminoethyl, diethyl 2-hydroxypropyl amine ethyl, carboxymethyl, and sulfopropyl. Among these, when you move from this blue side to green side, the probability changes from anionic exchanger to cationic exchanger, because these two are generally negatively charged, so they will help cations to exchange. These are positively charged, so they will help anion to exchange. So these are strong anion exchangers, and coming to these are strong cationic exchangers. So these are the examples of stationary phase which will be coated on that polymeric inert resin and used as exchangers. Mobile phase in ion exchange chromatography. Mobile phase comprised of ions that are to be separated. What are the factors affecting the ion exchange chromatography? Respect to mobile phase, the flow rate of the mobile phase, chemistry of the mobile phase, ionic strength and concentration of the mobile phase. No matter, we are always saying since HPLC and paper and TLC that mobile phase is a carrier, but always into inverted comma, I have told that they also interact with the analyte. And when they interact with the analyte, what are the affect factors of mobile phase that will affect your sample? They are chemistry of the mobile phase. If your mobile phase is more catching your sample, then it will affect the interaction between the sample and the stationary phase. Keep this point in mind. Aqueous acids and base solutions, as well as organic and non-aqueous solutions, are generally used in mobile phase. So this is a benefit. You can use water-based solutions and you can use non-aqueous solutions both in mobile phase as mobile phase in an exchange chromatography. And henceforth I told that in lanthanoid contraction example it was hydrated because that particular mixture can be prepared in hydrated form, aqueous solution. Ion exchange chromatography instrumentation. When I talk of ion exchange chromatography instrumentation, that instrumentation is very much similar to HPLC because here what we are doing, we are changing the column. I have explained it earlier in HPLC that four different types of mechanism are possible in HPLC, and this is second mechanism among that four after reverse and normal phase in the last lecture. So no need to remove mobile phase reservoir, no need to remove pump, no need to remove injector port. Only the first change comes is this ion exchange column instead of a reverse phase column or a normal phase column. Second important point over here comes is suppressor, then detector and then data system. So here there is a mutual benefit for you and me that few points will get repeat and so no need to go in much details. But friends, I have few interesting things to commit with you today. In the last feedback that came on day 3 results has executed very important points that sir we are less knowing about the injector although you have explained it. So it has to be in an animated form as you have given us few animations on day 1 and day 2. You are right. I had an animated video of the injector but I had purposefully kept it for an exchange chromatography because the main theme of ion exchange and RPC and NPC, that is reverse phase chromatography and normal phase chromatography, are different based on their mechanism, but both are used by a same instrument panel or a channel. And henceforth, I divided half of the instrumentation explanation yesterday and half I will add today. So the length is also maintained. Although yesterday we went for 70 minutes. So over here, today I will focus on that injector of yours. Friends, we will not focus more on mobile phase reservoir, only a little information. In ion exchange chromatography, the mobile phase system similarly can be isocratic, gradient, anything, but I have added something new over here that is to be carried forward from HPLC. Solvent system can be 2 solvent, 3 solvent, buffer solution means that particular point. But the reservoir over here, apart from glass bottle, can be a newer material that is in practice since last 5 to 10 years. That is PEEK bottle. Now this PEEK is a special polymeric material which is inert to most of the solvents and it is elaborated as polyether ether ketone material bottles. So keep this new point in mind. PEEK material bottles. So they are also inert, no corrosion, nothing. And prior of using the mobile phase, yesterday we had already discussed that degassing of the mobile phase is important. Vacuum treatment, helium purging, because this will help to avoid hard spikes or sharp spikes in the chromatogram. I told you, if impurity will go along with the purity in the column, you will get some humps in the column, and that will result on the data sheet. But that is not appropriate, so we are removing by the different methods of degassing. Now, focusing on the pumps in ion exchange chromatography, there are 3 or 4 different types of pumps in IEC that we have already seen yesterday as a part of HPLC. But the role of pump here is to deliver the mobile phase from reservoir to the ion exchange system with a constant and desired rate. If you recall yesterday's pump section and today's pump section, you can now judge the way I am presenting that yesterday I was focused on the type of pumps. Today, I am focusing on the mechanism of pumps. And when you will join both, you will be little more satisfied with the HPLC and ion embedded or ion exchange chromatography embedded in HPLC for the explanation of pumps. Over here, a solvent selection valve is there. You have a selection programmer and mobile phase, which was there yesterday in high pressure gradient system as a pink color mixture, from where you will select the different solvents. You can use a single or a double piston pump, but the piston of the pumps must be inert. You know, piston moves like this to and fro. Must be inert material because it will touch the mobile phase, so it has not to be reactive. And you avoid corrosion of removal of coating. Corrosion should not be there, or the coating of the piston should not come out. So now we will look into the phenomena how a piston works. Have a look at the animation as for your demand. How a pump works or how a piston in a pump works. Look at it.
The flow rate through the interaction with the slider bar. The flow rate is changed by changing the speed of the pistons.
You can see you can change the speed of the piston, which will result in the through flow of the mobile phase. You can see over here is a mobile phase reservoir. This is the piston in the pump and it is going towards the injector port. So friends, over here somewhere would be the injector port. This is the piston inside the pumps, and over here is a mobile phase reservoir tank. Let us just look at it once again. It is sucking the mobile phase from the reservoir and throwing it with pressure towards the injector.
The flow rate through the interaction with the slider bar. The flow rate is changed by changing the speed of the pistons.
And you can even change the flow rate. You can increase the flow rate, you can decrease the flow rate. Flow rate affects the separation. You have just now seen that what are the factors of mobile phase that affect the separation. Flow rate affects the separation. So friends, this was about the pumps. Now, on the basis of your reviews and suggestions yesterday, today we have an animated video of injector port also. You know everything about injector port. You even know that it is made up of inert material because the loop of the injector port will be filled with the sample. So that material should be anti-corrosive. And you also know the load position and you also know the inject position. Let me recall once that load is a position when you are just filling the sample in the loop. At that time, mobile phase will be coming from reservoir, passing through the high pressure pump, going into the injector, but without interfering with the sample, yes, will directly enter into the column and through the detector will go into the data sheet. And as no sample is there, you will get a straight baseline. But friends, when you turn the knob manually into inject position, it will change its route, get diverted. It will take the sample from the loop and move away. So now the route will change from mobile phase to high pressure pumps, from there to the injector, from injector to the new diverted route, from the loop column, from the column to the detector, and from the detector to the data system. Over here, I have added the loops now in the injector. And this is now going to be displayed in a moment as a very good animation to make the concept clear. Over here you can see the red line indicates that mobile phase is coming in from the pump and directly going towards the column. Yet you are left to fill the sample loop also with the sample. And when you will fill the sample loop with the sample, only 10, 20 or 30 microliters will be filled and rest will go into waste. After that, you will divert the route and it will take the sample and move towards the column. So this whole story, what I am speaking, will be now deliberated through this animation. Enjoy the animation, and after that, still friends who yesterday mailed me regarding the detailed explanation of injector port function, still you have doubt, please ping me up again.
Often done just with a manual syringe, and then the sample loop is completely filled. Therefore, to vary the injection volume, the sample loop itself would have to be physically changed.
See now what has happened. Mobile phase is moving in its own way. It is not taking the sample with itself. And during the same time, a scientist or a mentor or a student fills the loop with the mobile phase. Now is the time to change from one position to other. So friend, you can now judge that this is load position. Why? Because in the load position, you are only loading the sample. The sample is not getting injected into the column. And the minimum functions of the mobile phase are running. That is from mobile phase to pump, from pump to injector, without interfering the sample going into the column and from column to detector and from detector to data system. But as and when you jump from the load position to inject position, see the magic in the animation that happens. You could see the route has changed. The mobile phase has now taken the sample and it has moved. And again it has locked. Again it is locking, so the old system will start. Friends, this is how an injector port works. I am repeating it once more because I know animations are interesting and it makes the engineering concepts more clear.
Often done just with a manual syringe, and then the sample loop is completely filled. Therefore, to vary the injection volume, the sample loop itself would have to be physically changed.
You can see the diversion very, very clearly. Now the mobile phase is passing through the sample loop and going towards the column. So your analyte is going to be separated. Friends, before moving further, I have an announcement over here. I sometimes get suggestions that, sir, the video is not in a proper resolution. It is not so. And even if it is so, I might have corrected. But there is a way of learning on YouTube online. If you look into the YouTube videos directly on the web, sometimes they look blur because of some compatibilities, technical compatibilities. But if you download that video, store in your mobile or laptop, and then you look, I guarantee it will look clear in resolution in respect to the quality of the videos that my backup team is uploading. And even then, if you have any problems in the same, please let me know. Now let us move further, as I am sure that you might have learned and enjoyed the working of injector port. Friends, the column, that is the resin, the stationary phase, can be a cation or an anionic exchangers. The net surface charge of the resin, a cation or and anion. The resin or matrix of the column is positively charged, then the negatively charged ion will bind to it and vice versa. Separation depends on pH of the mobile phase, buffers, salts, organic solvents, and temperature during the experiments. But as of now, as it is a basic on IEC, we will just stick to the basic mechanism and not going into each and every details. Friends, types of columns. Over here, you have a main column which is called a separating column. But along with this main separating column, over here you have a facility of guard column. So first of all, we will learn of the separating column, and then we will understand the importance of guard column. Separating column is the main column, the heart of ion exchange chromatography, where ion exchange occurs depending on the surface charge of the resin, anion exchangers, and vice versa. But guard columns are placed before the main column, separating column, just with a purpose of increasing the lifespan of the column, because the columns are too much costly. So the guard column is used as a separating column for a prolonged life. It filters the particle responsible for clogging of the separation column. Means sometimes if degassing is not done properly, the particles will enter into the separating column and it will destroy this column, which is somewhat around 20,000, 30,000, and into lakhs. But to protect it, these are a type of filters that will not allow that impurities to come in. So it filters the particle responsible for clogging. If not filtered, affect the sensitivity, might give false peak, and resolution also decreases. Friends, this explanation can also be made in HPLC. Even in HPLC, people use guard column. And at the end of the column, there is also another material used. We call it FRIT. FRIT. But as I told you, the topics are somewhat similar in the form of instrumentation or engineering. I have divided the topics into 4 different lectures. In one, you go with the type. In other, you go with the extra things of that topic. So friends, what are the material used in preparing the column? It can be of glass, it can be of stainless steel, it can be of titanium, and nowadays researchers are also focusing to prepare those from the peak material. And what is peak material? Today you are knowing because I have already shown you the elaborated form of PEEK. What are suppressors? One of the most important part. Sometimes you get a background noise on the data. The baseline will move little up and down. It will not be proper because of few impurities or few technical or electrical errors, because these are, by the way, detectors, suppressors, pumps are, by the way, electronic gadgets, electrical gadgets. So the suppressor reduces the background conductivity of the chemicals that is used to elute analytes from the column, thereby helping in the accurate conductivity measurement of sample ions. It means sometimes what happens, the samples that are coming through the column carry with them few unknown ions present as impurities in the solvents. So you get their peak also. So this suppressor suppresses those unwanted ions and only allows or only focuses or only judge the ions that are of our interest. And hence it gives us a clear result of the ions of our interest or the analytes of our interest. These suppressors are membrane-based devices that converts the ionic eluent to water in order to improve the sensitivity. Sometimes you take buffer solutions, they have ions and that ions interfere. If you are taking acetate buffer, you can use acetate buffer in mobile phase in IEC. Then acetate ion will interfere, sodium ion will interfere. So you will get a peak of sodium ion, you might get a peak of acetate ion, and it will give you a false idea. So suppressor will suppress those ions. So background conductivity of the eluent, baseline minimization, which I told you earlier, optimize signal to noise ratio, increase detection and sensitivity, and these are the roles of a suppressor. So the suppressor is the new part, new introduction in our ion exchange chromatography. Detectors. In this aspect, before moving into detail, friends, I want to discuss something. I had got a very good suggestion yesterday, and even this suggestion came during my early talks last year. That, sir, can you elaborate the detectors in detail and the roles of each detector in details? I want to make it an announcement, or rather a clarification, that you will get the chance where I'll be explaining all the detectors only, separately, under a topic, detectors in chromatography. which detector can be used for what sample. Similarly, someone has given another suggestion that please elaborate on the applications of chromatography or HPLC in thorough detail. Yesterday itself I have told you that we are going to come up in later with a huge presentation on only applications of HPLC. So you will have someday in very near future two different presentations, applications in HPLC and detectors in chromatography. As of now, sample exiting the suppressors enters into a detector that is connected to a computer where resolutions of peak are obtained. Types of detectors include electrical conductivity detector, amperometric detector, and mass spectrometry detectors. There are many other detectors that can be used in IEC, but let us now focus on these three. And as I have told you, no detailed explanation of detectors as of now because we are going through a very brief discussion on the instrumentation part. Quality of detectors, low drift and noise level. They should be highly sensitive. Even the ppm and ppb concentration of ions can be detected. Fast response, low dead volume for minimum broadening of peak. The peak should be sharp. It should not be a broadening. I don't know whether you know or not. There are two interesting chromatographic terms when you get a peak. A peak that bends in the starting. Peaks are generally like this, but there are few peaks which look like this, and there are few peaks that will look like this. When a peak is bulgy in the starting, you call it fronting. Generally, you go like this and come like this, but sometimes you go up and come down. When you are going up and that peak is a bulgy one, you call it fronting. And when the peak that is coming down is a bulgy one, you call it tailing. So over here, the broadening of peak should be minimum. Insensitive towards the flow rate and the choice of mobile phase. Whatever be the flow rate, whatever will be the mobile phase, your detector must not be affected by those. It should always detect and analyze ions and give a perfect data. Simple to operate and highly reliable. If you are finding for few ions, your detector should always throw the right data on your data system. So friends, the quality of the detectors, let it be electrical conductivity detector, amperometric detector, or mass spectrometry detector, it should have anyhow these qualities imbibed in it. Scope of ion exchange chromatography. Ion exchange chromatography can be used for the investigation of cations, anions, and metal ions. It can also be used for charged biomolecules which I told at the initial slide. Nucleotides, amino acids, and alternative polar molecules, and evaluation of raw materials, conflicting impurities, and cleaning solutions. Also, this has a wide scope because it is average in cost, it has an excellent performance, and it has a huge sample handling property. Apart from this, chemical and pharmaceutical industries use this technique. Even petrochemical industries and food and beverages, even clinical and metallurgical firms use ion exchange chromatography because of these many scopes that are present. If I have a sample having cation impurities of arsenic, ion exchange is one of the good mechanism or an instrument to get out with the good result. So these are the scopes of ion exchange chromatography. Types of analysis that can be done in ion exchange chromatography. Qualitative and quantitative analysis of cations and anions. Trace and ultra trace analysis of heavy metals, ions. If you know very well, I'll give you a very basic example. There are few diseases that happen in the water. I will not give the name of a cation. You just go on the easiest tool available nowadays, Google, and find out. There is a disease called Minamata in this disease, there is a metal ion responsible. And to detect that metal ion present in the pond, lake, or sea water, ion exchange chromatography is used because it is present in a very trace or ultra trace amount, and it can be detected using ion exchange chromatography. So this is how you can detect trace or ultra trace analysis of heavy metal ions. Even mercury poisoning can be detected. Lead poisoning can be detected using ion exchange chromatography, both quantitatively and qualitatively. Ion exchange in combination with size gel filtration, hydrophobicity, that is RPC, reverse phase chromatography, and biological activity on the basis of affinity chromatography are also involved in ion exchange chromatography because of charged biomolecules. So these are the different types of analysis that can be conducted in ion exchange chromatography. Applications of ion exchange chromatography: purification of water, conversion of hard water to soft water. You know that removal of hardness of water is done by cation exchange and anion exchange resin. So over here, softening of hard water, demineralization of water, and removal of interfering radicals can be done by ion exchange chromatography. In this picture, hard water is coming from the inlet and soft water is going out as an outlet. If you see the hard water coming in, it brings with it green color particles which are in square as well as very tiny triangle particles which denote magnesium and calcium ions. Along with them, you can see sodium ion already present inside as cation exchangers. Means this resin is coated with sodium ions. When the flow of water comes with magnesium 2 plus and calcium 2 plus, this calcium 2 plus and magnesium 2 plus will get trapped on this ion exchange resin, which itself will be negative but will hold positive. So when you are negative, you are a stationary phase, and you are holding positive, you are called cation exchanger, although you yourself are negative. So it will hold calcium and magnesium and throw out sodium. So sodium containing water will come out, and as magnesium and calcium are trapped inside, it is called conversion of hard water to soft. Applications of ion exchange chromatography in several industries: industrial sample analysis, determination of heavy metals in cement, determination of petrochemicals like amines, mineral acids, cyanides, analysis of metallurgical components like steel and alloy, analysis of alkaline earth metals, sulfur, and chlorine in paper industry. So now over here you see, when you want to analyze chlorine or when you want to analyze sulfur, they themselves are negative. So you will require some positively charged stationary phase to catch them. So your stationary phase will be positive charge, but you are going to stick to it a negatively charged material. So this, although it is a positively charged stationary phase column, it is called anionic exchanger because chloride is going to come and stick. So remember these funda very well. Applications of IEC in environment, a very interesting part. Analysis of acid rain and rainwater. You can detect the carbonate content. Analysis of terrestrial water, ice cores from Antarctica. Determination of inorganic ions in soils. Phosphorus as phosphate, sulfur as sulfate, and nitrogen as nitrate. So these are some very interesting applications of ion exchange chromatography in the field of environment. Friends, applications of ion exchange chromatography in food and flavors. It is used in the determination of heavy metal limitations in dairy products, evaluation of sulfate, chloride, nitrate, and phosphate in sweeteners and sugar syrups, acid content in lactic, malic, citric, and acetic acid in coffees, food, and other beverages, fluoride content in tea, detection of glucose, lactose, and galactose in dairy products, arsenic in rice, and phosphoric acid in cold drinks, amino acid content in specialized nutritional product, and presence of carbonate in drinking waters. Over here, I have only mentioned the points, but few minutes before what I was telling was this, that I am going to come up with a total presentation where I'll be explaining each of these application with their mechanism or with their content, how it happens and why it happens. As of now, the topic is not application of ISC. The topic is itself IEC, Ion Exchange Chromatography. So this is the way I can explain. Applications of IEC in pharmaceuticals. In pharmaceuticals, separates the cations in water solutions for injectables. You know, the injection liquid contains some cations, but they should be in a proper amount. Analyzing final drug formulation. IEC provides a simple approach manufacturing process of drugs, and very important, IEC provides the easiest approach for the segregation of ions in decongestant and analgesic drugs. So it can also help you to combine different ions, or it can also help you to separate different ions. Here combining means it will not join them physical, but it will help you identify that your sample contains calcium, your sample contains magnesium. Let it be there in the drug. They are important from the drug, and now you can segregate that drug. This is how it is applied in pharmaceuticals. So friends, starting right from the background of ion exchange chromatography, coming towards the definition, principle, the stationary and the mobile phase, what are resins, the best example on ion is the potential value depending upon the charge divided by radius, the instrumentation, the excellent function animation of the pump and the injector, moving towards the column showing the exchange, and coming towards the applications of ion exchange chromatography in pharmaceuticals also. Moving towards some miscellaneous applications. It is used in scientific research to a highly extended level, cosmetics, clinical analysis, and bioactive natural products. So, friends, these were most of the miscellaneous and particular application of ion exchange chromatography. Advantages of ion exchange chromatography. Average cost, huge sample handling capacity. It is easy to handle and you can scale up from 1 gram to 10 gram and 100 gram. Non-denaturing process, high selectivity, it is eco-friendly, and the resin life is very long. So these are few advantages of ion exchange chromatography. Such a stuff happens sometimes. If you are going on the same track from HPLC to IEC, from IEC to GCN, from GC to SCFC, all are used in the same system instrument with only few changes, so there might come some repeatabilities. To avoid such repeatability, I divide four presentation in such a way that I'll keep few things of pump in one, few things of pump in second presentation, few things of pump in third presentation, and similar way of each component to make it interesting and avoid repetition of the topics. These were the advantages of ion exchange chromatography. Thank you, friends, for watching the ion exchange chromatography with huge patience. I know you all are doing really well because it comes to know from the suggestions and the feedbacks you are throwing on me. The questions that are coming is also imbibing me or forcing me to read something, to go on the websites to search and revert you back. Still, I am not able to answer all because still I am busy with few other things and to maintain your class. But I am sure I will satisfy all with your doubts. If I miss any of the doubts, you are free to bang me with the doubts. I will be happy to solve them. So once again, friends, thank you. Keep the video properly so you can use them in future. As I told you, if someone is facing quality problem of the video, it might be because you are watching it directly on the YouTube panel. You download it and then watch it in your mobile or laptop. I guarantee the quality is best. Thank you once again. If you have any queries in ion exchange chromatography, you can ask, and now you can move forward for the test. Thank you.